Hi, a few weeks ago I shot a video of refurbishing this Enertec function generator. I was jolly happy with it, and then this arrived from Defpom. Now in this original video it's very obvious, but when I look at the scope directly I just can't really see it. Perhaps there's some interaction between the shutter and the scope screen making it more visible. My multimeter though finally gave me the stats, and there is 1.2 millivolts of variability in the peak voltage. I'd hoped to keep this as a budget cost for a beginner to buy. Expensive capacitors would add quite a lot, so after visual inspection I kind of hoped to hang on to them. So I spent some time looking for leakage and deformity, and in the back of my mind I knew there were some voltage test points that I could actually test the ripple on. In fact, I had this to say. We do have a useful point here for me to check all the voltages, so that's great. I will do that. And I simply forgot to come back and do it. So measuring the rail voltages of course comes first, but then a look at the ripple on them as well can be very revealing, although you do need a differential probe if you're going to avoid picking up environmental interference. Anyway, once the doubt had set in, I just decided to replace them all, although I did do a few tests and I'll show you a few of those in a moment. Okay, so I've pulled the larger capacitors. 22,000 microfarad, 16 volts, 3,300, 40 volts, and 2,200 at 25 volts. Oh, and this little one, which is 2,200 at 16 volts. So most of these aren't difficult to get hold of. They can be a bit pricey. Now, what I'm going to do is have a quick look at the ESR and the actual value of the capacitors. The pinout, of course, is a little bit of a problem. Let's just zoom in a bit. So you can see that these are 3 ground pins on the periphery and a center active pin. Same with these, same with this one. Now, for these, the replacements that I've ordered, which are all very low ESR, long lifetime capacitors, they of course just have 2 normal, these are quite small capacitors, they just have normal leads coming out the end. Same with the 3300s. And for this one, which is the 22,000 16 volts, which I'm replacing with a 22,000, I think it's 35 volts actually, ultra low ESR. This has 4 pins, of which actually only 1 and 3 are connected to anything. These are actually just floating pins. I say they're floating, they might not be floating in the can, they're floating on the board, they're not connected to anything at all. So anyway, 1 and 3 are the pins of interest to me. The replacement for this is a clip-in. So it has 2 little bent tabs on the bottom which literally clip into holes in the board. So I will have to think about how I'm going to mount that. I will probably make a little board that I can put it into. Okay, so my capacitors and my boards have arrived. So these are just little adapter boards. So these enable these 3 pin to be converted into 2 pins, or conversely of course 2 pins to be converted into 3. So here for example is my new 3300, and these are Cornell Doublier, and they're only about sort of 30 milliohm resistance ESR, and these are 50 volts. So I bought a pack of these so that I've got a few in spare once I've finished. But these are clips, and they're set at 10mm, which doesn't match anything on the board. So I've made these little adapter boards, so these will clip into there, like that. And then the outer ring has 3 fixing points, which matches the 3 fixing points on one of these. So essentially, yeah, we convert our slightly more modern, slightly smaller capacitor into one of these using these adapter boards. And also I'll be putting a little plastic safety ring underneath as well, just to lift it off, just so that any solder connection cannot connect through to the board, because there's no solder mask or anything like that on the actual PCB on the system. So yeah, so I've ordered these. JLC PCB made them for me, they panelised them for me as well, because panelizing around things can be a bit of a pain. And yeah, they'll adapt multiple different types of capacitor, because if you're going to make one of these, you want to make it multi-use, not just for one specific job. So it'll take all sorts of different size capacitors and convert them into all sorts of other footprints. Super. So here's the meter that I'm going to use. It's a BK Precision 891. And yes, this has been calibrated, and it will measure ESR down to very low levels very, very accurately. So let's start off then, I guess. Let's have a quick look at one of the 2200s that I removed from the system. So if you recall, I said that the ripple actually wasn't that bad. It was there, but it was relatively small. So we're not expecting these to be disasters. So I'm measuring this at 100 Hertz because that's the frequency I'm going to use it at. And our 2.2 is coming out at 2.7. So this is 2.2 millifarads. And it's coming out as 2.7, 2700 microfarads. And that's a little bit high. And its series resistance 67.4. I would expect that to be about the 40 or 50 mark, something along those lines. Now, is that okay or not? Well, I'm going to go for no, it's not. I think the capacitance being high, if we think about the actual model of a capacitor with its resistance in parallel as well as resistance in series, then one of the reasons that the capacitance reads high is because that parallel resistance is dropping. In other words, the capacitor is starting to leak energy between its plates. And that means it's actually warming up slightly more than it should be, dissipating more heat than it should be. And that's a downward kind of trend. So it's probably okay. It's probably working all right at the moment, but it's probably just going to get worse. We'll put a 3300 in. So the 2200 is a 25 volt job, and I'm replacing these with some United Chemicon at 35 volts, and again just a big bag of them so that I have a few spare afterwards because they're a useful size. Same with the 3300, I'm replacing those with 63 volts. These are 40 volts jobs, and yeah, again I will be buying, or have bought, excess, so I have some for spare because again they're a useful size. So let's have a look at this. Now this one is looking in better condition, 3.4 millifarads instead of 3.3 millifarads, 35 milliohms. I mean, yeah, probably this is all right in truth. Yeah, I mean, I kind of would expect to read low with the capacitance if it was brand new. Let's put a brand new capacitor on, find out. Now, the ESR on this might read a bit high because I'm reading at 100. So this is a 3.3, brand new, and we can see that its capacitance is reading below the 3.3. And kind of that's what I'd expect to find. The ESR is reading a bit high, and one of the reasons for that is that it's difficult to make an accurate measurement of ESR at the lower frequencies. What you should do is just increase the frequency so that the capacitor becomes, this is a combination of the impedance that it measures and then calculates capacitance and resistance from, is a combination of multiple capacitance resistances and inductances. So essentially at the moment at 100 Hertz we've got enough there to measure capacitance pretty accurately, but the resistance is going to suffer because of the precision of the ADCs and things like that. So if we increase our frequency, then the reactance of the capacitor will essentially fall, and the resistance will be a larger proportion of what we are measuring. So we can do that. So if I make that 10 kilohertz, there you go, we can see that R is now about 30 odd milliohms. Now the actual, I think it's rated at 30. Now the actual data sheet from the manufacturer for this one specifies you measure the ESR at 100 kilohertz. There we go. So we can see that at 100 kilohertz or whatever, then it's about the 30 milliohms. So why has it gone up? Now I've gone to 100 kilohertz. Well, that's because the inductance in the leads and things like that is starting to have more of an effect. And earlier in the video I think I said it pins 1 and 3 or something like that. It's actually, there's a ground pin and pin 1 are what we need on here on this biggie. So this is supposed to be 22,000, and after some problems computing we've ended up with 27.38. Now 27.38 is pretty high, so again that's almost certainly the fact that the parallel resistance, which is of course leakage, is a bit high. So that makes the reactance, because it's in parallel with it, look a little bit lower than it actually is in the capacitance section. And since we're in a series resistance model, it can't compensate for that. So therefore more current is passing through the capacitor. It thinks, and it thinks therefore that the capacitor is a larger value than it actually is. The series resistance of course is absolutely fine. Let's put this onto and measure the DC resistance across this capacitor. It might take a little while, because essentially this has got a charge up from 0 volts on the capacitor. Okay, and we seem to be stuck at 819.3. Now given the voltage of the capacitor, that gives us a leakage current at operating voltage of about 20 microamps, and that's a little bit more than you would expect. But isn't so much that it would contribute a huge amount of ripple. Nevertheless, the capacitor is dissipating more than it should do, and is on a downhill path. So it just remains for me to stick a load of capacitors into these and then solder them into the actual board. Start with the awkward one that's buried, in this case, underneath the transformer, just off screen I'm afraid. Yeah, just under here. I'm going to start with that one because if I put this next one in, it's going to be completely in the way. So yeah, okay. Let's get on with that. I'm not going to show all of this soldering because it's really going to be quite tedious. So just turn this on its side, because this is the space where the first capacitor is going to go directly underneath the transformer. So it's one of these guys, and I just want to check the pin out and everything, and also just clean up the bottom if it needs it with a bit of desoldering braid. That could actually do with a slightly larger tip than this. No, 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 no! Soldering iron tips are not cheap. I've just lost one. Unbelievable. So I should have a tip that's a size bigger than this basically. And I can't find it. And that is going to make life very tricky indeed. Because the thermal transfer is going to be a little bit limited. So I just want to clean up this pad just here. And it's always just worth this extra little look, I think, because, for example, on this one, we've got 3 ground points around it. You can just zoom in a little bit, it might just... So here we go. So this one just here, we've got a centre pin and then we've got 3 ground points around it, but it looks like only one of them is actually connected. 2 of them are connected to anything. So I just need to make sure I do connect up to the right ones. So we are ready to go. And yes, just as before, I will be saving my little snips. So while it's still slightly warm, is the easiest time to do this. Just get your isopropyl alcohol on the surface and wipe it off with your Q-tip. And often that will be sufficient. Q-tip. Cotton bud in the UK, Q-tip I think in the US. I think that's right. Please correct me if I'm wrong. And somewhere I've got a little brush. I just can't find it. Yeah, and often I'll take this little brush and then just give it a good brush round. And we are clean. Excellent. So now I need to join up this guy. So this one just here is the big 22,000 microfarad, which is this boy. And we can see that actually two of the connectors are connected to nothing at all. Just here, this one here and this one here. And actually on the original capacitor they're not connected to anything either. There's only pin 1 and 2 connected to anything. And there's our ground and here's our plus. Unfortunately, it's easy to work out what's what because they haven't marked the plus and the minus on the boards at all. They've just kind of assumed you know. Oh. There we have them. Whew. So, okay, they did fit quite nicely. The pins are quite tight, but no complaint about that. Now I just need to get this ground plane. And putting plenty of solder on there because I want it to go all the way through and onto the other side. Okay, this one won't be so difficult. Excellent. So the isopropyl alcohol I use on here, and the reason it doesn't evaporate instantly off the warm surface is because it's actually only 70%. It's actually dissolved in a little bit of water. Which just means it doesn't dry out instantly. Cool. So I've got no concerns about the length of those pins coming through, that's absolutely fine. And I just continue with this in a logical order so that nothing gets in each other's way. So I've got my first multi-pin one in. Let's see how it goes. So I'm just going to let the soldering line feed in quickly into the joint and move out. I don't want to hang around too long on these if I don't have to, although there are some big ground planes on the other side, so I just do have to leave it there for a minute or two. Generally speaking, the flux will come off easier while the joint has still got a bit of warmth in from the soldering iron. I'm not talking red hot, of course, just a little bit of warmth. So yeah, so back here I've got a couple tucked away, but they're not interfering with anything else. So I'm going to pop those on, and then I've just got a big one down this side to fit in as well, which is one of those 3 pins, awkward little sods. So let's get the 2200 jobs in. Okay, so it's just a case of reassembling this now as carefully as we can. If I can persuade these bloody screw holes to line up. This is all just on standoff, so they're a little bit wobbly underneath until they're screwed in both ends. But I do want to get them in because on boards of this age they do sometimes actually use these chassis points as electrical contacts, and that can be a bit of a pain in the bum if you don't have them all joined up. It's not that often, usually it will work without, but you know, let's not have more things on our plate than we have to. So I'm just taking a moment to just visually check everything before I move on. Okay, all appears well there. So I'm going to finish reassembling this and then we'll see if we can see any difference. So here it is after we've got the capacitors in there, and I'm looking at this both on my studio monitor and the scope itself, and I cannot see any wiggle in that whatsoever. So there is a little bit of thickness at the bottom here. I've got a reasonable amount of persistence on at the moment, which indicates there is a little bit of jitter, but it's certainly, I think, within scope. So I'm going to call that done in terms of refurbishing this device. I have changed those capacitors out now, so that's good to go for someone. If they want to further refurbish that, replace all the rest of the capacitors, really connect this to a good AC digital voltmeter or something like that, and really trim it in tight, then that's fine. But as far as I can see, all the frequency, the amplitude, the amount of ripple and noise on the amplitude, the harmonics, they all seem to be pretty good. Anyway, I hope you enjoyed that. If you did, don't forget to subscribe, like the video, tick the bell if needs be, and yeah, see you next time. Bye for now.